All right, welcome ladies and gentlemen to the video for 6.3 parametric equations. We're going to be looking at a little bit more usage of our calculator, some things you've never seen before on your calculator, and obviously specifically here the parametric equations. And let's kind of go ahead and see what parametric equations are going to be. So they are often used to model and investigate, if I could read, motion of objects. So one of the big things we're going to do at the end of the lesson is modeling, I think, a baseball and its flight through the air using some trigonometry, some parametric equations, that sort of idea. Now, the thing with parametric equations, parametric graphs, it's the graph of ordered pairs x, y, just like normal. The difference is each variable, x and y, have their own functions. And t is the thing that we're going to be inputting into both of these functions. I'll get to that example in just a second. T usually represents time. So as time goes forward, the horizontal, you remember the x represents horizontal. As t goes forward, the horizontal motion is doing something, and as t goes forward, the vertical motion is doing something a little bit different. So usually, like for a baseball, the horizontal motion is just going straight across, where the vertical motion is doing a parabola style function. All right, so if I was to give you this problem here, a rock dropped from 420-foot tower can be represented as the function y equals negative 16 t squared plus 420. Now, if you were to graph this particular function, you would get something along the line of this, where my y-intercept is 420, negative 16t squared tells me it's a parabola moving downwards. The problem is if I just dropped the ball, or rock, I guess, if I just drop the rock from 420 feet, this is not the motion that the ball will take. This particular graph would be time and height. So it would be height over time. So as time goes on, height is decreasing. However, if I was to truly drop the rock from 420 feet, it would go straight down. And we can model that using the parametric equations. And I'm just giving this to you, by the way. Parametrically, we can graph it using x equals 2.5, and 2.5, as I mentioned here, 2.5 is just a random number. If I used x equals 0, then it would be on the the y-axis, and that wouldn't be very interesting. You couldn't see it. So what I kind of want you guys to do, if you guys have a calculator with you handy, I want you to graph this. So you're going to need to go and change some modes and all that sort of stuff. And I think that's on my next page here, if I recall correctly. But essentially, we're going to get this. The ball starting at 420, and it's going to decrease down to 0. The thing is, you're going to have to change some stuff. So here's what I want you guys to do. If you have it handy, if you don't have it handy, write this down so you guys can do it in class with one of my calculators and just practice this concept. We're obviously going to change the mode to parametric. That's down by function, polar, parametric, and sequence, I think it is. And since t usually represents time, we usually start with t equals 0. For this particular question, we're going to go to a max of 5. So t min is 0, t max is 5. I'm going to do this right along here. Oh, by the way, this right here, this stuff, I didn't mention this here. This is in your window. So t min of 0, t max of 5 with a t step of 1. What this is saying is I'm going to start at 0 seconds, I'm going to go to 5 seconds, and I want it to take a calculation at every second. So if you could figure out the height at every single second, you could create the points for this graph. And then x, remember x really doesn't matter, but since I used x equals 2.5, I need 2.5 in there somewhere. So 0 to 10 is fine with a scale of 1. And lastly here, because the height of the ball has to start at 420, I might as well go all the way up to 450 and start at 0, go 450 with a scale of 45. Some of you realize why I use 45 there. It's just so I have 10 tick marks on my graph. It's no big deal, actually. That's not a big deal. Then if you go into y equals, oops. If you go into y equals, and you'll notice, since in your parametric mode, you're going to get x and y for each of your graphs. So under your x1, you're going to type in 2.5, and under your y1, you're going to be negative 16. Now, you notice that this is a t. Up on the top of your calculator where you used to use the x key, you'll notice that it's actually the x t theta in key. And since you're in parametric mode, it knows to say t. So if you use the x button, the normal x button, it's going to say t. So t squared plus 420. And if I go to graph, pay attention to the graph because it's actually looking like the motion and it drops straight down. The line drops straight down. It didn't go vertically because that's not what the ball does. It goes straight down. Some little fun things that you can kind of do is if you go to y equals and you go to the left where it gives you the color, if you're on the color version, or that little line, you can change the line to a ball and just a ball. And I'll kind of go over this a little bit in class as well. But if you change it to just a ball, then you can actually see the ball or the rock just drop straight down. That's not really important. That's more just kind of a cool little visualization thing that you can do. All right, so you should have, like I mentioned there, you should have on your graph now something that looks like this in your window, and it started here and went straight down and stopped right there. It doesn't even hit the x-axis there. Okay, so you could also trace this if you wanted to trace and you want to say, hey, what was the height at time equals 3? So I go, okay, let's trace, and I go to t equals 3. If you just push left or right, obviously to the right to go upwards in time, it says y is 276. So that means at time equals 3, it was 276 feet above the Earth. All right, so let's try another one here. Let's try x equals t squared plus, or sorry, not plus, t squared minus 2, and y equals 3t. So go back in, type those things in. Let's see if the window works here. I don't think it's going to. So if I just said t squared minus 2 and 3t, and I go to graph, it doesn't really look very nice. If you just kept the same window, you're going to get something like this. All you see is this little line that comes up here like this. That's about it. That's not very interesting. So as you get more familiar with these type of functions, you'll know how to figure this stuff out. So what I want to do first is I want to change your t, so t min to -3. Now this is just a math problem, so it's okay to have negative time here if you want to think about it that way. If it's a real world, then you don't go to negatives. So -3 to 1 with just a step of 0.1, I think. I'll look at that in a second as I graph it. This represents, by the way, this is a x window, so your x min is -10 and your x max is +10. Your y min is -10 and your y max is +10. And just go on x and y, just do steps of 1. And for this particular graph, if you did everything correctly, you will get something along this line, kind of like almost a sideways parabola. And if you did this a couple of different times, and if you changed, notice if you had from -3 to 1, you get this function, or this graph, and if you changed your window from -3 to 3, you actually get a continuation here. And what you might notice is this actually kind of looks like a quadratic function, only it's on its side. And here's what you guys should be paying attention to. This was one graph. You did not have to graph two different lines, which meant the parametric mode can graph non-functions. It's actually handy in certain areas. Okay, so for this -3 to 3, you should get something a little bit like this. And you'll notice that this is -2 here on your x-axis, which means you're actually graphing a sideways parabola. Notice this, t squared minus 2, it's sideways, and the -2 is your vertex. All right, so that's kind of just an introduction onto the parametric mode. There's a couple of things we need to do with the equations from this before we get too complicated. The first one is what we call eliminating the parameter, which means we're going from parametric mode to rectangular mode. So from a parametric equation to what we would call a normal equation, a y equals or something like that. An example would be this. So here's a parametric equation, x equals 1 minus 2t and y equals 2 minus t. And what we want to do is we want to write it in terms of like this. Like y equals, maybe it's a linear function. I don't know yet. Y equals mx plus b. That's kind of what I want to write it as, a normal equation. So what we're going to do here is we're going to look at first this. We're going to say, let's get t in terms of x. So I could, however you want to do it, I can say 2t is equal to 1 minus x, and therefore t is 1/2 minus 1/2 x. And then if I know that t is something, well, I have a y equals, so y is equal to 2 minus 1/2 minus 1/2 x. So I get minus a negative half makes a 1/2 x, and 2 minus a half is 3/2. And there you go. If you were to graph this parametric equation on your calculator in parametric mode, you should get a graph of the line 1/2 x plus 3/2. What about this next one? Same idea. I want to eliminate the parameter. So for us, let's just keep going with the same theme here. Let's get t by itself with the x. So I get t squared equals to x plus 2. I get t is equal to plus minus the square root of x plus 2. And I get y equals 3, actually plus or minus 3 times the square root of x plus 2, because that's t, which technically means it's two equations, 3 times x plus radical x plus 2 and -3 times radical x plus 2. And if you recall, that's the one we did a little bit ago. And if you were to graph this back into rectangular mode, square root of x plus 2 is over here, goes this way since it's and the 3 just makes it steeper. And the negative version goes this way, and you'll notice that we get that sideways parabola. That's not necessarily the only way we could do this, but for now, for us looking at the x and then the y, that's what we want to do. Next one here on the same kind of idea is 2 cosine t and 2 sine t. And this one's kind of hard to solve because you don't want to do cosine inverse. Because cosine inverse is not going to get us the right thing. But if you were to graph this particular function, you will get this. Well, that's kind of interesting. Kind of looks like a circle. And you should be saying it looks a lot like a circle because it is a circle. And there's reason for that. obviously. I'm trying to graph this here, 0 to 2 pi. Window, come on. Why is my calculator not working? Huh. My calculator will not graph. That's very interesting. Let's try a different calculator. Okay, hang on here. 0 to 2 pi, scale of 1, negative 10 to 10. Oops, quit. Mode. Sorry about this, guys. Parametric. Well, anyway, I don't know why mine's not graphing. But anyway, I was just making sure that this was a 2. So it crosses at 2, which means my radius is 2. Well, that's interesting because there's some 2's here. That might be kind of nice and interesting. But here's how we're going to do it. We know that sine squared and cosine squared and all that sort of fun stuff and circles has some x squareds and y squared. So what we're going to do here, when you see problems like this, 2 cosine of t and 2 sine of t, you're going to do this. You're going to say x squared plus y squared. And I know that x squared, x is this, so x squared is 4 cosine squared plus 4 sine squared, which is equal to 4 times cosine squared t plus sine squared t. And you will probably recall that cosine squared plus sine squared is 1, and therefore you get x squared plus y squared equals 4. Okay, it's really simple, but notice it has nothing to do with cosine inverse. Don't use cosine inverse. It doesn't work. Use this very simple Pythagorean identity. All right, next, we're going to find the parametrization of a line. So I'm going to give you a line, or a line that goes through 2 points. And what we're going to do is we're going to figure out how to write the parametric equation for this line. So it's kind of complex here, but what we're going to do is you're going to say, hey, let P be some point that's on the line, and it's between the points A and B. And let the point O be the origin. So I couldn't get the vector symbol here. So these are all vectors. So note that we learned some vectors the other day. The vector OP minus the vector OA is equal to the vector AP. That vector is actually a scalar multiple, so it's just a number times this vector of AB. We need the component forms of these 3 vectors. And then we're going to use this very, well, relatively simple formula. So this is pretty key. And we're going to solve for each component, which means we're going to solve for x and we're going to solve for y because we need some function with t and some function with t so we can look at it as parametric mode. All right, so I have my example on, oh, I forgot to delete it, on my next page here. Okay, so let's think about the vector OP. Since P is just a point, the vector, and this is kind of long wording for this, but the vector is just, since the point xy, going from the origin to that point, the vector is just xy. And then OA, oh, sorry, I did the wrong thing here. This is the problem we should be doing. -2, 3. and 3, 6. I wrote the wrong problem down. I ended up actually writing the answer down. Oh well, we'll get the answer. So A is the point negative 2, 3, and B is the point 3, 6. Okay, so the vector OA is just, since that's a point going to the origin, it's the vector negative 2, 3, and OB is the vector 3, 6. Easy peasy. All right, so here's what we have to do. We want OP minus OA. All right, so vector X, Y minus vector negative 2, 3 is equal to T times the vector OB, okay, 3, 6, minus the vector OA, so negative 2, 3. So this is just using that thing that I put in the bubble on the back side, on the other page. This new vector, since it's just subtraction, just becomes x minus negative 2, so plus 2, comma, y minus 3. It's equal to t times the vector. Okay, 3 minus negative 2 is 5. 6 minus 3 is 3. So I get x plus 2, y minus 3 is equal to 5t, 3t. Well, for equality of vectors, that means the first piece equals the first piece, and the second piece equals the second piece. So x plus 2 equals 5t, and y minus 3 equals 3t, and I just have to solve for y. So y is 3t plus 3, and x is 5t minus 2, and you notice we get the answer that I accidentally gave to you before we started. All right, it's not hard, you just have to practice the skill. All right, so let's get into what I think is the most fun stuff from this particular lesson. It's projectile motion, so we're looking at how something flies through the air. All projectile motion is going to be written like this in parametric mode. X equals v sub ot cosine theta times t. And y is equal to negative 16t squared plus v sub ot sine theta t plus y sub ot. Well, it might be a good idea to know what some of these things are. V sub 0 is what we call the initial velocity, and y sub 0 is the initial height. So you're going to be given an initial velocity, an initial height, and a theta. So look, you never get away with trig. You're never going to leave trig, by the way. And theta is the angle made with the horizontal. So like if you hit a baseball, it goes at a certain angle from when you hit the ball. So here we have this guy, Eric. He hits a baseball that's 3 feet above the ground with an initial velocity of 100 feet per second at an angle of 18 with the horizontal. And the question is, will the ball clear a 20-foot wall that is 400 feet away? So this becomes kind of complex here, but nothing we can't do. So we're going to write some equations. So x is equal to v sub 0, which is initial velocity, which is 150, times the cosine of my angle, which is 18 degrees, times t. And y is equal to the equation, negative 16t squared, it's just there, plus initial velocity. Oops, not times the cosine, times the sine of 18 degrees, t, plus my initial height, which is 3, which sounds about right because you hit the baseball around your waist, about 3 feet off the ground. And what we can do is we can graph this function. What's really cool is it will graph just like this. So we need to figure out some time values. For the most part, we're just going to go, I think it's 0 to 3 if I recall correctly. So we get 150 cosine of 18. Make sure you're in degree mode, obviously. And negative 16t squared plus 150 sine 18 t plus 3. I go to my window. I change my t min from 0 t max to, let's go 5 just to be safe. T step of 0.1. And here's where you got to change your x min, x max. Well, x min, that's a horizontal distance. So I'm going to start at 0. And I need to look at 400 feet away from the plate. So I'm going to go to 450 just to be safe. And I'm going to go again by a step of 45. Your y min, y max, not super important, but y min, probably ground level, which is 0, and y max would, let's just go to 100. Well, when I graphed that with those numbers, I said x min is 0 and max is 450. And y min is 0 and max was 100. I get a graph that looks like this. And what you can do, and it actually touches the x-axis here, what you can do, again, is you can trace. And if you go out to x equals 400, which is kind of hard to do, actually. But I can zoom out to, or not zoom, I can trace, and my trace will bring me out to x equals 399.4. And you could probably estimate pretty good. And you'd notice that the y value is 7.35. So that means at 399 feet away from the batter, the ball will be at 7.35 feet off the ground, but it needs to clear a 20-foot wall, so the answer is no. It will not hit a home run. Eric's not hitting it hard enough. And you can kind of tweak these equations around. Let's say you hit it with 180 feet per second at this angle. Would that be enough? You can just change this ever so slightly. Okay, I'm going to leave it at that. I am going to leave you with these, and I hope we come in tomorrow ready to work on these parametric equations and really look at the motion of baseballs, golf balls, footballs, that sort of stuff.